terms of number of landmarks and number of particles.
So we have to do it for each particle.
Exactly. So it should be
Linear and the number of
exactly. So it's quite like to be linear in the number of particles. Absolutely right. What about the landmarks? Does it depend on the landmarks?
The odometry does not update, does not depend.
Perfect. So there's no dependency on the landmarks, the motion step, so it should be just linear in the number of samples. What about integrating the observation into my belief? Why n times m?
Because each particle has to not n, because n not observed particle. Just I mean n number of observed particle.
Okay, so observed. You mean?
Observed landmark, and then multiply with the particle.
Okay, so the number of particles times the number of observed landmarks. If we assume we do every landmark separately, it's absolutely right. We have the number of it's linear in the number of particles, because every particle needs to update. I have the data association, so I just basically look up in an array of, this is landmark number 10, so retrieve landmark number 10 and update. It doesn't depend on how many landmarks I've stored there, if I implement in that way. Resampling. How expensive is resampling? So how expensive was this low variance resampling, which I explained last time? It was linear in the number of samples. But, there's a big but. So the resampling procedure itself is linear in the number of samples. But in the worst case, I need to copy the samples, duplicate a sample. And duplicating a sample means copying the map. And so this is the resampling step now turns out to be the most important, computationally most demanding operation in the standard simple particle filter based implementation, because it's the number of landmark particles times the number of landmarks. Because maybe if all particles have a weight close to 0 and one has a weight close to 1, it's quite likely that this particle will be copied n times, and then I have an n times m computational complexity. So this is kind of the computational complexity for every iteration for a simple implementation of FastLAM. Still, it's just linear in the number of landmarks, which is actually quite remarkable if you compare it to the EKF. But we can do better. We can do better by using, by not changing the algorithm, but just by using a smarter data structure. Instead of saying, okay, every particle maintains its an array, let's say, where it stores all the, or list where it stores an array, where it stores all the landmarks. I take a smart tree structure, a binary search tree, where particles can share landmarks. As the landmarks are all independent of each other, if I update some landmarks in this part of the state space, I typically don't change the landmark somewhere else. It's not as in the EKF where an update here can change the uncertainty of all landmarks everywhere. There's something which I don't have here because I have this conditional independence given the poses of the robot, so given the sample. So what I can do is I compute, I take a search tree. It's not a simple search tree. And so just say, okay, I'm looking for, let's say, the landmark number 3. So take a search tree, okay. Is it smaller than 4? Yes, I go here. Is it smaller than 2? No, I go here. Is it smaller than 3 or smaller or equal to 3? Yes, I found my landmark number 3 here. It's just a binary search tree. No black magic. Every one of you should have heard that in Introduction to Computer Science 1 or Algorithms and Data Structures. So, and this has a complexity which is logarithmic in the number of landmarks that I have. So I can access a landmark in a logarithmic complexity. What I now can do is, I can say, okay, Now let's do exactly the same thing. Let's particles share those estimates down here. And then the tree gets a little bit more complex. So say I have my old particle. So this was at the previous point in time. And I have a new particle, which comes, let's say a particle is duplicated from the resampling process. Okay, it's a new particle. Then I can build, for the old particle, I can build, have my standard tree as it was the case. And for my new particle, it references into the old tree. And whenever something is updated, just this updated path is replicated and then stored locally. So only if I update a landmark, and this is a constant number of operations I do every point in time, I need to kind of store here now 2 different estimates of landmark number 3, but all the rest is shared. This requires some bookkeeping to do that, what has been updated, to which particle does this estimate kind of belong to, but you can, in this way, can do that that copying can be done very efficiently, and then the only thing is that retrieving a landmark, it's a complexity which is logarithmic in the number of landmarks and not constant anymore. As a result of that, this step, integrating an observation, gets more expensive. It gets the factor log m. But the resampling gets cheaper, and so the overall complexity is cheaper. It's the number of landmarks of particles that I have times the logarithm of the number of landmarks that I need to maintain. So this is, of course, the computational complexity. Memory complexity is larger because I still need to, of course, maintain all landmarks. You had a question?
No, I only had a mistake on the last slide. On the right side, we have the same as on the left side. In the last line with the J, it's 1 and 3 on the right side.
Yes. So this is definitely a copy-paste error when making this figure. So this should be 5, and this should be 7.
Yeah.
Absolutely right. 5 and 7. Yep. Okay. Let's look to the memory usage of this algorithm. And so the memory usage is dramatically reduced for using this smart tree structure because you don't need to replicate the number of the landmark estimates for all particles. And you can nicely see that kind of the log n complexity is here along these lines, and the linear FastLem, which copies for every particle the number of landmarks, has a complexity which grows linearly with the number of samples. And kind of how steep this increase is just only depends on the number of particles you have, because the number of particles is constant. And so if you have more particles, you would have a steeper increase here, but it will be still linear. Okay, so that was kind of FastLem 1. Now you know everything about FastLem 1. And I just want to use now the next 2 to 3 minutes to explain you what FastLem 2 could be, or at least tell you what the improvements will be, because then in the next lecture we will look into how to build maps with grid maps with these particle filters, and then we actually look into kind of FastLem 2 for grid maps, because for grid maps this FastLem 1 doesn't really work for some reasons we will explore next time, but for landmark maps it's operational, it works, but FastLem 2 for grid maps is then the solution. Therefore I said, okay, I don't go into FastLem 2 for landmarks, just do FastLem 1 for landmarks, and we do FastLem 2 for grid maps next week. But at least I would like to give an idea how we can do better. So what FastLem 1 does, it says, okay, we take as our proposal distribution our odometry motion model. And the question is there a better way to do that? Obviously, if I ask such a question, there is a better way to do that. How could you imagine a better way for doing that? How can you do samples better? Better means that you draw the samples only in the kind of high areas of high likelihood or regions of high likelihood of your state space. There's a technique we discussed last week which may help to inspire you in doing that. The end of the grid mapping chapter. Scan matching, maybe?